on these particular interconnects. And then the last portion that I want to show is some examples in real designs. And I think this will be very helpful for illustrating some of the concepts that we'll discuss. So let's just jump right in. I'll do a brief intro into what are differential pairs for anyone that is newer. And I like to start with this diagram where, of course, we show the fields being generated by differential pairs. Here we have two signals, equal and opposite polarity, that we were trying to send down a pair of traces on a PCB. This is shown in microstrip configuration, of course. And these two signals could have some DC offset. When current is being, is traveling down the interconnect, we actually have electric and magnetic fields that exist around the trace that are really responsible for carrying the energy. Here you can see the direction of the magnetic fields being generated around the trace. And in each case, they are essentially equal and opposite so that you get constructive interference between the two traces. But the fields die off or destructively interfere outside of these traces. So here on this edge and here on this edge. So that's very important because it illustrates one of the reasons that we originally started using differential pairs to transmit very high speed signals at very high data rates. It's because farther away from the differential pairs, you get less noise. Now you don't get zero noise, but you get less noise because of this destructive interference between different portions of the electric and magnetic field outside of the pair. Now, as these signals travel along the differential pair, they of course have some speed. The speed is dependent on the dielectric constant, the real part. For microstrips, we have an effective dielectric constant because some of this field exists in air. And so you have something like an average. It's not exactly that, but it's kind of like an average between the dielectric constant of your substrate and the dielectric constant of air, which is very close to 1. And so that gives you, for a DK approximately 4 laminate, you get an effective dielectric constant of approximately 3. And that puts the signal speed at about 100 million meters per second. Actually, no, a little more than that. Sorry about that. A little more than that. For strip lines, here we just use the actual dielectric constant. Again, it's kind of a weighted average when you have this situation where you have the DK here and the DK here being different, but it's going to be very close to the average of these two values. And so that's our signal speed. So the signal speed is simply the speed, literally, at which the signal travels. But what's actually being contained in the signal? Well, the signal contains data, of course, and typically we don't have a separate clock in serial interfaces. The separate clock is a artifact, or not an artifact, but kind of left over from the days when we had system clocks or when everything was source synchronous. So if you are familiar with SPI, you'll know that SPI is source synchronous. But what actually happens in high-speed interfaces is the clock will be embedded in the data stream. So the first few pulses in the data stream will be the clock, and the receiver latches onto that and then uses that for its timing. This is defined using an encoding scheme. Manchester's one coding scheme is defined in this IEEE standard. Typically, you'll see like 8B, 10B, meaning the first 2 bits are clock, and there are a variety of others. So if you want to read about encoding schemes in serial data transmission, you can go look at the Wikipedia article on it because it has a lot of information. So I brought up, 802.3, which most of you should recognize as the standard for Ethernet. So there are various Ethernet standards, and kind of the base standard is 802.3. But there are others where the clock will basically be embedded. So with LVDS, USB, I believe JESD 204, essentially there's only 2 wires, and kind of the idea here is that you contain everything in those 2 wires. Now, that's not the only kind of differential interface, but it is very common. And when you're looking at these very fast pairs at 100G or higher, you will have embedded clock inside that differential pair. But there are also groups of pairs in interfaces like CSI2. So in CSI2, this is used for cameras. So for retrieving high-speed data coming off of a camera module, CSI2 uses groups of differential pairs, and then you have a clock differential pair. So you have a dedicated clock, kind of like you do with DDR. This dedicated clock is its own differential pair, and you can see that here where my mouse is on these two vias coming off of an FPGA. And then you have these other lanes that also transmit data. So you have these 4 lanes in a single CSI interface. So together you have length tuning, as you can see here, within a single differential pair. But then you also have to maintain timing across all of the pairs. And so that's where the signal velocity becomes important, because now you have to maintain timing across all of these such that the bit streams on these differential pairs arrive at the receiver within some time window. So you will sometimes see large length tuning sections that apply to both of the pairs. And I believe we may have some examples later on. So those are the different ways that we route data and clock in a differential pair. Now, what's happening at the receiver? So when I say that the signal velocity has to be known, it's because you need to determine some length mismatch allowance. So the length mismatch allowance is being compensated here in this one pair with this section. But then again, you also have to match across all the different pairs with a different length tuning allotment. So here, where we have our reference voltage, this reference voltage is basically our DC offset, and it can be 0, positive, or negative. Typically, it's 0 or positive. But here what's happening when these two signals on a differential pair arrive at a receiver is they need to just cross each other at the same time. And that's because differential receivers are basically just crossing detectors. And that's how they interpret a logic signal embedded in a serial bit stream. And so this time, delta T max, is defined by the allowed crossing window between the positive and negative polarity signal that's traveling on one of those traces. So you should use a delay tuning tool if you know this time window. However, if your CAD software does not have a delay tuning tool, you can still use a length mismatch rule. You just need to know the velocity of the signals that are traveling on these interconnects. So you need to know the velocity of a single signal and its complement on this opposite pair. And then you need to know the velocity of the entire interconnect. So basically the velocity of the merged signal. Okay, so it's pretty simple. And again, your CAD software can be used to determine this. So for example, Altium Designer does it. I believe OrCAD does it. And then there are free tools out there on the internet that will give you a very reasonable value and tell you the V value. The delta T can be determined usually from data sheets. In fact, there may be an allowed skew specification in some SerDes, drivers, and receivers. And that will tell you this delta T max. And so that delta T max multiplied by your signal velocity basically gives you this delta L. Now, you could have different velocities for each of the traces on one of these pairs. And so this gets into one of the myths and facts, which I'll discuss earlier, or I'm sorry, which I'll discuss later. But that myth is that you have to always route them on the same layer. And that's not exactly true. You can route two differential or each trace in a differential pair on different layers. And as long as the signals arrive within some time window, then the interface will still work. So sometimes what you will see in a data sheet is you won't see this delta T max at all. You'll actually see a delta L value. So there will be a skew allowance specification, but it will sometimes be in length. And typically it will be something where it says like 100 mils or 150 mils or something like that. Usually that number is totally arbitrary. Whoever wrote the data sheet just kind of pulled it out of thin air and said, 100 mils is good enough. We'll just use that. And they usually did that because their test data probably showed that they could definitely operate within much larger than that number. So they're just going to give you a conservative value of 100 mils. So just be careful when you see nice round number for length tuning tolerances specified as a distance in a data sheet, because that number could be totally made up. Now, what happens with the termination on the device? Well, a lot of devices have different termination schemes. And what I'm showing here in the top right circuit is one termination scheme where you have a threshold voltage or a reference voltage defined using pull-ups. And then these pull-ups are used to terminate the incoming signal coming off of these differential pairs. And so each of these traces has a specific impedance called the odd mode impedance. And I'll explain what that is later. But it is not always the same as the differential or as the characteristic impedance. Excuse me. So typically what you will see if you look on something like Wikipedia is you won't see any kind of complex termination circuit like this. What you'll actually see is they'll just put a resistor here between these two pairs. That is classic LVDS. And when I say classic, like back when it was first introduced. And that's not exactly correct. And it doesn't really reflect how a lot of differential interfaces have to work. Also, this circuit doesn't take account of things like equalization in the receiver, which is one of the important tools that's built into integrated circuits in order to allow you to resolve data from a very noisy bit stream, especially when you're at these very high data rates like 100G and higher. So there's additional stuff in this termination circuit that allows you to resolve the data that's coming across this differential pair. But you'll notice that this is for a Stratix device, so an FPGA. So a lot of FPGAs will have these different termination circuits built into different IOs. And you're basically programming all of that when you create the image for your FPGA. Okay, next, materials and stackups. So materials are very important in PCBs, obviously. They are constructed from this fiberglass weave that is embedded into an epoxy resin. And this epoxy resin and the fiberglass weave have different dielectric constants. Now, in a perfect world, they would always be the same. And I'm sure there are people out there working on materials research that are trying to find some materials that have these matched dielectric constants, but they don't. And because these different materials, the resin and the fiber, have different dielectric constants, the result is that a signal traveling on one of these traces in the differential pair could have a slightly different velocity from a signal traveling on another of these traces in the differential pair. So you can see that here in this left part of the diagram. And what that does is it causes the two traces to slowly come out of alignment. So when the two signals come out of alignment, eventually, if they get too far out of alignment, they can't be read as the data can't be recovered from those signals at the differential receiver. Now, there's something else that happens once you get into the 50 gigahertz range, and this is in the PAM4 range. So now when you're operating at PAM4 224G interconnects, you have another issue with open weaves, which is called periodic loading. And periodic loading was first noticed in RF systems where you are basically just sending a harmonic signal or a modulated signal along one of these traces. Oh, sorry about that. And what they noticed was that they were getting big dips in the return loss and big peaks in the insertion loss spectra for their signals. And the big and small insertion losses that you see in those spectra correspond to resonances. And so they called this periodic loading, meaning that at different portions along the interconnect, you would essentially get excitation of these resonances in this structure, and that would lead to strong losses at certain frequencies along one of these traces. So first noticed in RF, but now with interconnects operating with channel bandwidths at least 56 gigahertz in order to hit PAM4, now there's a chance in order to hit 224G at PAM4, now there is a chance that you could also see this same effect in differential pairs. So the solution here is spread glass, Or you could even have some fun and do things on like PTFE with no glass and do something unreinforced. So those designs are much more difficult. But spread glass is a really simple way to do this. And spread glass is available from a number of different manufacturers, including low loss versions of these laminates from vendors like Isola. So there are a lot of fabricators that will stock that or that can get it, and they can build these types of designs on spread glass for you. So exactly how much skew is too much? Well, just going back here, it depends on this interface, right? The interface needs some timing window, and you need to ensure that you allow for enough skew in time between those two signals. So that's why it's a good idea to length match as close as possible, because there's going to be some additional skew anyways. So the additional skew does come from the fiber weave effect, but there are other sources of skew. So the sum of all skews, according to Steve Corrigan from Texas Instruments, is known as jitter. So he was the one that defined jitter as the sum of all possible sources of skew. So the big one for differential pairs is, of course, this fiber weave effect. However, there are many other sources of skew that can cause two signals to become misaligned over time. And so having your traces length matched very close to each other is not necessarily required. However, it's a good idea to have the two traces or to have the two signals cross each other as close as possible, because it allows you or gives you some margin of safety for any of these other effects like the fiber weave effect. Okay, now the fun stuff. Some myths and facts about differential pairs. So, differential pair, myth number one. Differential interfaces will only work if pairs are routed together on the same layer. So I brought this up earlier. If we have two different velocities here for our signals on these traces, then they may not align in time. What matters is that you get the signals to the receiver at the same time, and it doesn't really matter how you do that. As long as you do that, the interface will still be able to interpret the data from that pair of signals. So this gets into tight coupling, and I'll get into what that means in just a second. But here, we will just want to make sure that the signals arrive at the same time. And so what that means is that if we have different velocities on different layers, we may need to apply some length tuning on the other layer. Now, there are advantages to routing things on the same layer, and there are advantages to doing things like tight coupling, but it's not required in order to interpret the data at the receiver end of the interface. So is there any problem here that might not be related to the function of the device? Well, sure, because we brought up things like noise when we first talked about what a differential pair is. So it's the reception and creation of noise that may be degraded when you take these two pairs and you don't tightly couple them. So there are reasons to tightly couple the traces in an interface, but it's not required to interpret the data. And if you want some proof, I invite you to ask Rick Hartley. He'll tell you a fun story about how he bamboozled an engineering manager into thinking that he did tight coupling on the same layer when really he took two traces in a differential pair and routed them on opposite sides of the board and probably put his own job at risk just to prove a point to somebody that said he had to use tight coupling in order for an interface to work. Okay, number two. Differential pairs and signals require or don't require ground planes. So this is a fun one because there are two versions of this myth. The myth is that you absolutely must always have a ground plane no matter what, or you don't need a ground plane ever, and you can always route differential pairs however you want. So there are reasons to have a ground plane. If you think about what happens on, for example, a signal being routed out over a cable, you could have unshielded cable without grounded copper going through that cable. There's no ground plane in that cable, but the cable still has a defined impedance. Well, why is that? Well, in the case where you have ground, like for example, this coplanar ground, the coplanar ground and any ground on the other layer will influence the impedance of this differential pair. But the spacing between the differential pair also matters. So the spacing between these traces can be used to set the impedance, and it can be used to set the width to a reasonable value. Now, for example, if your width is too large, even without a coplanar ground, you could still bring in some coplanar ground, and it will allow you to reduce the trace width. So now it's going to be much easier to route into this USB connector that I'm showing in this example. So this example here on the right it has a differential pair for USB on a 2-layer board, and we're trying to hit the USB impedance spec. So on a 2-layer board, you should probably know that it's very difficult to hit an impedance spec without coplanar ground. The reason is that the trace would have to be very wide. And in fact, the trace would have to be so wide that it's going to be unusable with most components. But when we have the coplanar ground here, and when we bring the two traces closer together, that allows us to use thinner traces, and then we can still hit our differential impedance target. So this illustrates one reason that we might want to use tight coupling, and we might want to use coplanar ground. It's so that we can hit that target and be able to route the traces together in a thin manner, or with thin traces, so that we can actually get into some of these components. So this is exactly why something like USB can work correctly on only a 2-layer board. You don't have to have a 4-layer board with all differential interfaces. You can do it on a 2-layer board. There are reasons to do it on a 4-layer board, but this one is a device that's done on a 2-layer board, and I've actually shown this one on a video on the Altium Academy YouTube channel. Next one. Differential pairs do not create crosstalk, and there's a corollary to this, that differential pairs are immune to crosstalk. And so if you regard these linear networks as reciprocal, then one of these myths should imply the other. The reality is that differential pairs do create crosstalk, and they can receive crosstalk. So we have differential crosstalk between differential pairs due to the mutual capacitance / inductance between these two. So they can receive crosstalk and give crosstalk to each other. The other thing that can happen is you could have, for example, a single-ended signal that is an aggressor into a differential pair, and it could create a strong crosstalk in one end of the pair, but weaker crosstalk in the other end of the pair. And so the result is that you basically have some differential mode noise that exists between these two pairs with respect to some virtual ground. And so differential mode noise is bad. Why is differential mode noise bad? Well, differential receivers cannot remove differential mode noise. But differential receivers, because they sense the difference between the plus and the minus signal, they can remove common mode noise. So common mode noise can be rejected up to very high values in a differential pair. Differential mode noise cannot. So we would like to prevent differential mode noise. And when you have this case where you have a single aggressor signal injecting crosstalk into a differential pair, that injected noise is going to be differential mode noise. So differential mode noise can only, or differential pairs can only perfectly suppress only common mode crosstalk. So that's an important point to note. And this will become important again when we talk about, mode conversion. Mode conversion is very important because it relates to the conversion between common mode and differential mode noise. Another myth and fact. The myth here is that vias must always be eliminated, or if present, they must always be back drilled. There are reasons to back drill vias, and there are reasons to eliminate vias on an interconnect. However, this idea that a very high speed interface will never work with vias is completely wrong. So just as an example here, I have some data on the right showing a stacked and staggered blind Berry via example supporting 112G NRZ signaling. So that's up to 56 gigahertz bandwidth, or 224 PAM4 modulation signaling. So this interconnect has a very low return loss all the way up to about 56 gigahertz. So this would be very easily able to support something in the 10 to 20 or 30 gigabit per second range, no problem. And then you could even get it higher into 60 or 70 or even higher once you apply a modulation format like PAM4. Now, since the newest data center architecture is targeting 224G PAM4, it's worth asking, can we use stacked, staggered, blind buried vias in these interconnects, whether it's coming off of, for example, like an FPGA or a TPU or a GPU, or whether it's coming off of a connector? And so the answer is yes, you can. They just have to be very carefully designed. And the issue here is that once you get the signal into this via and onto the receive side of the via into a transmission line, you have a problem in that you can get a lot of loss up to these very high frequencies. And so this is why we need things like equalization in receivers. It's going to allow us to recover the higher end of the frequency bandwidth up to these very high frequencies and overcome some of this loss that accrues in some of these via structures. Also, the insertion loss along these interconnects really limits the interconnect length on the PCB. Interconnect lengths are on the order of inches, and I don't necessarily mean like 5 or 10 inches, usually just a couple of inches, before you get to something like active copper, or you get to a fiber transceiver so that you can transmit the signal over much longer distances. But the point here is that back drilling is not always required. You could do stacked, staggered, blind. You could also do through holes and go all the way through the stack up with something like 224G or 112G. The issue with going through the stack up is that sometimes you're going to need a smaller via diameter. So can you fabricate that? Well, you have to see whether or not a 6 mil diameter can be mechanically drilled at your fabrication house. Some fabrication houses can or will do it. Others will not. And then that 6 mil via, depending on how far it goes, it may not be able to provide the low enough return loss. So it really depends. And new vertical interconnect architectures may be needed in your design if you are targeting these really high data rates. So now let's go into interconnect design. So this is the fun stuff. So what are the goals in differential interconnect design? Well, first, obviously, we have an impedance target to hit. I've mentioned this impedance a couple of times. There will be losses within that entire interconnect. And so you need to route the interconnect such that you stay within the loss budget, but you also need to select materials that allow you to stay within your loss budget. Then you want to ensure that there will be an open eye at the receiver. This is typically done with simulation tools. And of course, we want to prevent crosstalk, but we also want to make sure that we have minimal mode conversion. So mode conversion is very important for noise suppression. So I have presented this in several instances. I'm going to present it again, and I'll try to be brief. All transmission line impedance can be described using the RLCG model, as long as we are talking about quasi-TEM transmission lines. So non-quasi-TEM transmission lines is a topic for another presentation in the future. It's one I haven't prepared yet, but it's a very important concept. All transmission lines that are operating in PCBs, including up to these 224 gigahertz or 224 gigabit per second channels, are still quasi-TEM. So the RLCG model still holds. Now, the parameters in the RLCG model are the resistance, the inductance, the capacitance, and then we have this kind of, bogus resistance here that's meant to model the loss tangent or the dielectric loss in the in the PCB substrate. So the dielectric constant here is defined as having a real part. The real part defines the signal velocity, and then there's an imaginary part. And the imaginary part, the real part, and then the conductivity of the substrate, which we usually just take to be 0, gives us the loss tangent. If you look at data sheets, they always quote the loss tangent as a positive number. That is wrong. It is absolutely wrong, and I wish that people would stop doing it. They also put a negative sign here for the dielectric constant on the imaginary part. That's also wrong, and I wish they would stop doing it. So if you have any questions about why that's wrong, that's more of a physics topic, which I'd be happy to answer on LinkedIn. But there are a few material parameters in here that are very important that determine losses in the interconnect. So one of them is the copper roughness. So that's this K term. And this K is a function of angular frequency. So meaning it's a function of the frequency of the signal that you're trying to transmit through your interconnect. So just like here, we have our S parameters as a function of frequency. The roughness losses will also be a function of frequency. We also have a skin effect here. Skin effect can be determined from field solvers for unique geometries. It can also be calculated analytically, and there are some calculators online that will do it for you. Here in the capacitance equation, we also have this K sub G. This is basically like a fringing factor, and it defines the capacitance of a real interconnect with respect to an aspect ratio. So basically an area divided by distance above the ground plane. So all of these parameters play into the transmission line impedance and the propagation constant. So if we just plug all of this stuff into the transmission line impedance equation, we get something that looks like this, Z sub 0, for a single transmission line. So a single transmission line in isolation from all other transmission lines has a characteristic impedance that can be calculated using this formula. So I know it looks really complex, but at low frequencies, K is just 1. And here the loss tangent you can pull from a data sheet. R sub S, like I said, you can get it as a function of frequency, or sorry, not as a function of frequency, but you can get this R sub S term from some online calculators. RDC is easy to calculate. It's just using the cross section. And then L and C can be pulled out from a lossless model in your design tool or in some of these online calculators. Now, the important impedance value for a differential pair is not Z sub 0. It's not the single line impedance or the characteristic impedance. It is actually the odd impedance. So the odd mode impedance is the impedance of a single trace in the pair once you bring in the other trace and form a differential pair. And the reason we have an odd mode impedance is because there's mutual capacitance and inductance between the two traces that make up the differential pair. And so I've written that in here. We have this L sub M term and this C sub M term. And typically what you will not see is this big formula that I show here. Typically what you'll actually see is Z odd down here, written in this lossless form. Now, some people will also write it as kind of this coupling impedance, Z21. And then sometimes you will see this K coefficient here to define the odd mode impedance. So what is important here is that the odd mode impedance is always a little bit less than the characteristic impedance. So how much less? Is it just a couple of ohms? Is it 10 ohms? Is it 20 ohms? Well, we'll see some examples where it can actually be very large as we keep going. But the point here is that when you design the transmission line impedance, you are actually accounting for CM and LM. And you need to make sure that the calculator that you are using is actually calculating an odd mode impedance and not a characteristic impedance. So if you calculate the characteristic impedance of a line and you say, I have a 50 ohm transmission line, then you bring in another transmission line and you form your differential pair. Now the impedance of that line is not 50 ohms anymore. It's less than 50 ohms. And so the reason that's important is that you can then get excess return loss at very high frequencies, which is especially important when we're targeting these very high data rates at 112G or 224G. So how much of a deviation can we expect? Well, I've given here just a couple different examples of what happens when you have different spacing values between the two traces in the pair as a function of substrate thickness. So when the substrate thickness, meaning the distance from the traces to the plane, is very small and the spacing is very large, then your odd mode impedance and your characteristic impedance are very close to each other. So if you're at this 4 mil range and below, your odd mode impedance and your characteristic impedance are very similar when the two traces are spaced far apart. So this is one of the reasons to not use tight coupling. The reason you may not want to use tight coupling is you have very much smaller deviation between your characteristic and your odd mode impedance, as well as your common mode impedance. And I'll show examples of what that means later. Now, here, when you bring the two traces very close together, you get very big deviation. That's because you get a much larger reduction in the odd mode impedance. Well, why would we get a much larger reduction? Well, that's because C sub M is going to be much larger when we bring these two traces closer together. C sub M is our mutual capacitance between these two traces. And so when we bring these two traces closer together, we have smaller distance between conductors separated by an insulator, and that means that C sub M has to go up. So this is just the basic idea from capacitance. So that's why you see this kind of curve with the spacing between the pairs equal 5 mil to be far above the case with us with larger spacing. Now, this is without coplanar ground. Now, what do you think is going to happen with coplanar ground? Well, with coplanar ground, we might expect one of these traces to be brought down a little bit, and then that would bring our odd mode and characteristic to be closer together. Now, if you look at a differential impedance specification, typically they will be written like this: 100 ohm differential, 50 ohm single-ended. When they say single-ended, they're really referring to the odd mode impedance. So single-ended in this context does not mean differential impedance, or does not mean characteristic impedance. The reason for that is that the differential impedance is always double the odd mode impedance, always, by definition, okay? So really the only impedance that matters that you have to actually calculate is the odd mode impedance. That's the only impedance that matters. It's the impedance that matters for termination. And if you look back at the earlier termination circuit example for the Stratix device, you'll actually see that those termination resistors are sized to match the odd mode impedance and not the differential impedance. So the odd mode impedance is the only impedance that matters, including the impedance for impedance matching at a differential interface. Now, a bogus spec, I've seen these bogus specs, and a bogus spec will sometimes read 100 ohm differential, 50 ohm characteristic. This is impossible. It's physically impossible to have 100 ohm differential and 50 ohm characteristic impedance. It's physically impossible. In fact, the only way you can do it is if the two traces are separated from each other by a distance equal to infinity. That's the only way you will ever have this type of specification be true. So when you see this type of specification, ignore it. It is incorrect. What really matters is the odd mode impedance and not the differential or the characteristic impedance. Next, let's look at some signal integrity comparisons across different situations with differential pairs. So, differential pairs have losses. I outlined the two main sources when I was talking about the RLCG model, and those losses are the roughness and the copper. So the copper has some resistance because it is not a perfect conductor, and then the dielectric has some losses as well. So which of these losses are dominant? Which ones do we really need to care about? When do we need to switch from very rough copper to very smooth copper? The next question that we have to ask is, of course, what happens when we vary the geometry? If we have a pair and it maybe is creating too much loss for us, we decide to change the geometry. What happens when we change the geometry? What happens to the losses? Next question, what happens when we vary these different parameters? But we want to try to keep the target impedance fixed. That's very important in parameter variation, especially with differential pairs at these very fast data rates. So we're going to look at some of these different situations. So first, what is copper roughness? Copper roughness is exactly what it sounds like. It is the roughness of the copper film that's placed onto your PCB. Copper can be very highly roughened. In fact, copper will be intentionally roughened in certain layers in order to enable bonding between different layers and when the stack up is being built. And the exact structure of the copper will determine the model that you have to use to describe copper roughness. So unfortunately, without microscope images of copper foils, you generally have to assume what that copper looks like and what model you're using. So these roughness models have been explored pretty extensively in the literature. Here's one of the earlier papers from Yuri Shlepnev. Bert Simonovich is also well known as someone who has done a lot of work researching copper roughness. The copper roughness model is important because it allows you to determine what the true skin resistance is in your interconnect. So higher skin resistance means higher loss. And typically the skin resistance will just be given by some value. But once you have rough copper, the rough copper increases the skin resistance significantly. And there are these different models that are used to define what that effect is, or what that K factor is. So the K factor here for this example model I've shown here for the Cannonball Hurray model. And like I said, there are many different models. There's the Cannonball Hurray model, there's the Hurray model, there's the Snowball model. There are all sorts of different models. They have some interesting names. And they basically try to model what happens when you have these stacked spheres of conductors. And they try to model what happens to the skin effect. Also, what happens is you actually have a modification of the dielectric constant, and that causes a modification of the actual loss tangent, or the dielectric losses experienced by a signal traveling through this dielectric. So here we have essentially a corrected dielectric constant, and it can be approximated based on this 10-point roughness value. So the actual thickness of the dielectric as given between these flat lines across the film compared to the rough thickness, that gives you this correction in your dielectric constant. And essentially what it does is it increases the dielectric losses. So again, here's one of the papers from Bert Simonovich I'd recommend you go and read to learn more about these different models. There's also this one from 2018, very good paper on these different roughness models and why they're important and how to use them. Next, let's look at a comparison between copper and dielectric loss. So copper and dielectric loss, how can we compare these? How can we separate them from the propagation constant? Because remember, the propagation constant contains all of the information about how a signal moves along a trace. And it doesn't matter whether we're talking about the signal on a single trace when the trace is in a differential pair, or the sum of the two signals, meaning the sum of the electromagnetic field around those two traces in the differential pair. No matter what, we have a square root here that we have to use and apply to this product of complex functions. So if we take the product of these two things, we take the square root of this complex function, and then we break that square root into this real and imaginary part, we basically get these two terms for a dielectric loss and a conductor loss, and this is in dB per length. And what you can do is you can plug in some numbers here for different loss tangent values. So here I'm just using an example, dk 4.17, dk 0.014, and then different roughness values corresponding to, for example, these two different models. And then you can look at what happens to the loss values from each of these contributors. So what we see is that initially in the dielectric, we see that at low frequencies in microstrip configuration, the dielectric and the conductor loss can be similar. And that's even the case where we have roughness playing a role. Now, eventually, when we get to really high frequencies, the dielectric loss will start to dominate. But it's in that mid-range of frequencies where the roughness really matters. Now, let's consider something just for a moment. Let's suppose we are designing a very high-speed interface, but we want to use a low loss, a low dielectric loss material, right? Low dielectric loss material could have another zero here in the dielectric or in the dissipation factor, right? So just as an example, you can find advanced dielectric or advanced FR4 dielectrics where the loss tangent is, for example, 0.005, right? So if this were, let's say, 0.005, that's basically a factor 4 smaller, and that would get our microstrip losses down to about 0.015. Okay, and then we'd also have this this loss at the 10 gigahertz would also be smaller. Okay, so what the lower loss tangent is doing is it's extending the range of frequencies where the copper losses are dominant. And this is why at some point you have to make a transition from rough copper to smoother copper. So rough copper is more realistic, and kind of the basic values that you'll find for copper could have pretty high roughness. Eventually you can get to very low roughness values that starts to approach these limits for smooth copper in these interconnects. So even if you just use a low loss dielectric, you will still have some copper roughness that you have to contend with in these interconnects. And eventually you'll have to make a transition to low profile copper. So next, let's look at an example where we vary the geometry of a strip line. So here we have a strip line differential pair. We're hitting a 100 ohm differential impedance target in this example. We have 50 ohm odd mode impedance. Here are the different parameters. We have some roughness defined for the copper. We have a decay value, right? That's our real part of our dielectric constant. We have a loss tangent. And we want to ask, how do these changes in the geometry affect the impedance and the losses? And how do the changes in things like the dielectric affect impedance and losses? So here what I've done is I've created this table. And these tables show you what happens when you have different decay values and you make different changes in one of the parameters in each table. So let's start with the left table. Basically what the left table is saying is we're going to change decay to a new value. And in order to ensure that we continue to hit our impedance target, we're also going to change W to compensate for this smaller decay value. So we start with 3.5, we go to 3, and then eventually this goes down to 2. Now, for those of you who are familiar with PCB laminates, you might be saying, hey, DK2, that's not really readily available in these thin layers, is it? Not right now, it's not. Rogers has like a liquid crystal polymer material, but I think it only goes down to 7 mils, not down to 3 mils. However, there are companies that are working to get to DK2 laminates, and I know they're working on it because they have consulted with me about it, and that would then allow them to have these very thin layers that you see here. So where the dielectric thickness above and below the trace could be 3 mils or even smaller. So there are companies working on this, trying to get to that goal. Now, if we take the decay value and reduce it, and we increase the width in order to compensate, what happens to our dielectric and our copper losses? Well, here you can see very clearly that as we increase the width while maintaining the same spacing and dielectric thickness, the characteristic impedance gets closer to the odd mode impedance. But the characteristic impedance was already within 1% in this case. And that's because we had wide spacing compared to small dielectric thickness. So here, when we have this 3-to-1 ratio of spacing to dielectric thickness, we're going to have very low mismatch between the characteristic impedance and the odd mode impedance. And then as you can see here, with higher and higher DF laminates, of course, we get more total loss. However, as you move from left to right on the table, as we increase the width, you see that we get smaller and smaller loss. And that's to be expected. Now, what happens if we change the spacing? So let's say we want to keep our width the same for our traces. And there are reasons you would want to do that. For example, BGA breakouts. There are reasons that you should keep that width small. And in order to compensate for this change in decay, we decide we're going to bring the traces closer together. We're going to reduce S. So when that happens, eventually your characteristic impedance starts to get very large. And if you don't keep track of the fact that you're working with odd mode impedance, not characteristic impedance, you might eventually find that, hey, my characteristic impedance is 66.7. I need to change something in my interconnect in order to hit a characteristic of 50 ohms. Remember, characteristic doesn't matter. The odd mode being 50 ohms is what matters. Now, in this case, where we decrease the spacing in order to compensate for this change in decay, we see that initially we get a little bit of a drop in the losses, but that kind of saturates pretty quickly, right? So when we go from 3.5 to 3, as we move from left to right along one of these loss rows in this table, we see an initial drop in the loss, but then we see that it pretty quickly saturates, and we can stop expecting to see a decrease in the loss. Now what happens when we change the thickness of the dielectric? So in order to compensate for this change in decay, we go to a thinner dielectric. Well, in that case, we do also get the change in the characteristic impedance becoming closer to the odd mode impedance. But now we start to get an increase in the loss. So you can see here as we move from left to right, we get an increase in the total loss, despite the fact that we have kept W the same. So what we're actually getting is an increase in the dielectric loss along this interconnect. And that increase in the dielectric loss results in these higher values that you see moving from left to right along the table. Now, here I've kept RZ as 0 in all of these instances, but you should already know what happens when we increase RZ. RZ is our roughness, and so if we increase that, then we know that all of these values in this lower half of these tables is going to also increase. Okay, next, I want to talk about length or delay tuning, really the same thing. So we already talked a little bit about length tuning and delay tuning. And I mentioned that it's a very good idea for reasons of accounting for skew overhead to have the signals lined up with each other in time as close as possible. And that generally means that they need to be the same length. Now, what happens if we do this with a lot of length tuning sections? Now, remember, if we take a differential pair and we just route it straight from the driver to the receiver, we don't have any bends, we don't have any curves, and we're not trying to compensate for any bends or any curves, and we just have the true traces being the same length, well, how does that affect SI and EMC versus the case where we have a lot of mismatch and we need to apply a lot of length tuning structures to overcome a lot of turns and bends? So what we'll see here in this example is that sometimes it's better to have fewer length tuning structures than it is to have more length tuning structures. So let's look at what happens with the signal integrity in length tuning structures. What happens in length tuning structures is that length tuning skews common mode noise and basically creates something called mode conversion. Now here I could replace common mode with differential and you get the exact same thing. Length tuning also skews differential mode signal and turns it into common mode noise. It turns differential mode noise into common mode noise as well. So what happens here on the driver side is, let's suppose, for example, that on the driver side, I have a 5.66 mil width trace, 10 mil spacing. I've sized these traces here by this driver side to have odd mode impedance of 50 ohms. Well, I'm now routing this signal into a length tuning section. So for whatever reason, I need to have this big length tuning section, and this big length tuning section compensates for bends or something else elsewhere in this interconnect. So what happens when I route the signal into this? Well, here in these regions where the trace is farther away from this top trace, you have an impedance deviation. So the odd mode impedance in this region is larger than it is in this region where the two traces are closer together. And so the result here is that with this 21 mil amplitude, you get about a 3 ohm impedance deviation. Now, what happens if the traces are initially closer together? So instead of 10 mil spacing, we have 5 mil spacing. Well, now you can see that the impedance deviation in the odd mode impedance is much bigger. So now we get almost 20% deviation in the impedance. So that's going to be much more reflection as the signal travels from the driver side into the receive side. So the first thing that you get with length tuning structures is you do get some reflection. And the frequencies where you get the reflection become smaller when these length tuning sections are larger. And so that's why I say sometimes less is more when it comes to length tuning. If you can apply length tuning sections so that they are shorter, that will push the reflection that you expect to see up to higher frequencies. Next, what happens in length tuning structures when you have those reflections? Well, you will then see this in the differential S parameters, okay? So the differential S parameters are defined in terms of differential receiver side versus the differential driver side. And here, the differential receiver side is basically this entire load, and then the input side is located here on the left, okay? So first, we have reflection at high frequency. That's one reason that we'd like to keep these length tuning structures short. Now, what happens to the velocity? So remember, we have different characteristic and odd mode impedances. I'm sorry, not characteristic, but we have different odd mode impedances here in these sections of trace. Each of these sections of trace, just based on its width from in this region right here and right here, they all have the same characteristic impedance, but they have different odd mode impedances. And so this gets back to my point. The only impedance that matters is the odd mode impedance. And so when you have these length tuning sections like this, the velocity in the length tuning section is going to be slightly different from the velocity in the untuned section. So the signal velocity over here is 145.34 picoseconds per inch, whereas in this section where you have the large deviation in the length tuning region, you will then have a value of 148.89. So this is important because in this region, the routing tool incorrectly assumes that the delay is actually this value. So it doesn't take very many of these length tuning sections to create so much skew from your routing tool that you essentially misalign the two signals, especially in a very high speed interface like at 224G. So in 224G, we would like to avoid these length tuning sections as much as possible because we have very fast edge rates. When your edge rate in a 224G signal could be, for example, down at 10 picoseconds, and you have 3 picoseconds of skew for each of these regions, you can have at most what? 3 of these regions, 3 of these length tuning regions in your interconnect before you've run out of skew budget. Now, what happens when these two things are closer together? Well, when the two traces are closer together, remember, we already have bigger impedance deviation. We also have bigger skew deviation. So when the traces are closer together, we have even fewer structures that we can accommodate without hitting a skew budget limit. So this is another reason to ignore the tight coupling idea that everybody pushes in differential pair guidelines. Sometimes spacing them out is much better. And this issue with overcoming the skew in length tuning sections is one reason to have your differential traces spaced out from each other by 10 mils or even more than 10 mils. But what exactly is mode conversion? Well, as I mentioned, it's the conversion between common mode and differential mode noise. Now, let's just suppose for a moment that on this driver side of this interconnect, my trace receives some common mode noise. I don't really care how it got there, but let's just suppose that there is some common mode noise on this left side of this interconnect. Now, here, my signal plus the common mode noise travel through the length tuning structure. What happens? Well, some of my signal gets converted to common mode noise. And then when that signal reaches the receiver is going to cancel it. Okay. So what this length tuning structure is doing is it's increasing loss in my differential signal. But what happens to the common mode noise? Well, the common mode noise turns into differential mode noise. And remember, differential receivers can't cancel differential mode noise. They actually read to the differential mode noise. And if the differential mode noise is extreme, then it could blow through your noise margin and then you won't interpret logic states correctly. But what happens if my noise over here on the left side starts as differential mode and I have differential signal? Then I pass this through a length tuning structure and it converts to common mode. And then I take that signal plus the noise and I put that out onto a cable. Well, if I put that onto a cable, now that common mode noise is going to radiate very strongly. And it doesn't take a lot of current, as you can see from the values of this table, in order to create an EMI situation that causes EMC failure. So if you have common mode noise present as a current on a cable, even at these low frequencies, it really only takes microamps worth of current in order to create enough noise to then cause failure under these two FCC regulations. Now, at what frequencies does this start to become prominent? Well, it really depends on load capacitance, and then it depends on the phase shift along your transmission line, which means it depends on the spacing between these two pairs. So here you can see what happens when we have no length tuning versus the case where we do have length tuning. And I've looked at the mode conversion here in terms of the phase response from the transfer function of a transmission line. So you can see very clearly what happens to the phase response of a single transmission line when we have these length tuning sections included. And you can get a pretty significant phase deviation across these two traces at these very high frequencies. So this is yet another reason to ignore length tuning structures at very high frequencies. So at what frequency can we find acceptable length tuning structures or try to design acceptable length tuning structures? Well, what we need to do is we need to ensure that if we do have length tuning structures, they do not create excessive mode conversion up to the Nyquist frequency for our channel. So the Nyquist frequency is kind of our limit where we need to operate in these very high-speed channels. So in 112G PAM4 signaling, the Nyquist frequency is 28 gigahertz, and in 224 PAM4 signaling, the Nyquist frequency is 56 gigahertz. Now, this application note is from Intel, and I don't normally show application notes from semiconductor companies talking about issues in PCB design. However, they did a really good job of evaluating what they're showing here and showing whether or not it actually works, and then analyzing what happens on the PCB. So here, what they've done in this application note for Intel Stratix devices is they are showing here some possible solutions to the issue that happens in your CAD tool with applying delay tuning. And what they're also showing here is that sometimes if you have excessive phase mismatch, like you have in this graph that I've shown here for the transfer function for a transmission line, sometimes just one or two extra length tuning sections is enough to bring this phase graph back into alignment so that these two curves overlap. Now, as long as you don't create excessive mode conversion or excessive losses up to the Nyquist frequency, then you can do this. So how do you know whether or not you've done that? Well, you need to use an electromagnetic field solver to figure that out. Now, they also offer some tuning structures here where you can widen out the trace a little bit in the uncoupled region. The problem with doing this is that your CAD tools do not apply this automatically. These types of length tuning structures, as far as I know, I've never seen a way to apply this automatically so that it tapers out the trace in this region and then narrows it back down in this region. So if anybody knows of a CAD tool that will do this, message me about it on LinkedIn because I'd like to see it. But I know that the major ones that I use don't do this, or at least I've never seen a feature that does this. Okay, so the last topic I want to talk about is very important, and I brought this up briefly earlier when I was talking about some of the primary issues in differential interconnects, and this is differential vias. So vias in differential pairs are absolutely needed. At minimum, you will need vias to break out of an FPGA, as I showed in the example with the CSI interface coming off of an FPGA. So that is the minimum case where you will need differential vias. And I bring up breakout because a lot of these devices that are using these very high-speed interfaces are going to be on, for example, an advanced CPU. They could be on a GPU, they could be on a TPU, or they could be on an FPGA. So you could instantiate it in the FPGA using vendor IP or using custom logic. So the differential vias are needed to get those signals out of those devices. Now, what are the goals in via design? Well, vias have an impedance, and you need to match that impedance of the via to the impedance of the traces that the vias are connected to. And if the vias are coming off of, let's say, a connector or a module, or they're coming off of a processor, then the vias also need to match to the output impedance of that processor. And generally interfaces, high-speed interfaces on those devices are very well matched to 50 ohms, and you can take that as a reference. There are, of course, cases where you will need to measure that directly and simulate it for your particular system. So don't just take it as exactly 50 ohms at all frequencies. Buffers on integrated circuits have a capacitance associated with them, and that capacitance, as well as the package parasitics like package inductance, that will affect the output impedance from your buffer, and that could affect how the signal gets injected into the transmission line. But generally what you're measuring on a PCB is you are just measuring a signal that gets into a transmission line, and then you're trying to ensure that the transmission line is matched all the way across at all elements across the transmission line, and that includes vias. So how do you match impedance from a via to a transmission line or a load? Well, first things first, most via impedance calculators that you see online are absolutely 100% wrong. And in the cases where they are correct, they're only correct in frequency ranges where you actually don't need to worry about the via impedance. And I'll explain why that is here in just a moment. But the important takeaway here is that vias are actually treated just like transmission lines. And just like transmission lines, vias have an odd mode impedance and a differential impedance. So just like we only care about the odd mode impedance of the trace, we also only care about the odd mode impedance of the via. So we're matching the odd mode via impedance to the odd mode trace impedance that is connected to it. And that's what we're trying to match. That's our design goal. Now, I brought up stubs earlier. When should you remove stubs and can you get around back drilling? Now, back drilling is an expensive process. It's a controlled depth drilling process, and maybe it doesn't cost so much where you only have two vias that you need to back drill. But if you're dealing with a large number of high-speed interfaces coming off of an advanced ASIC or an FPGA, you could have dozens of stubs that you might need to back drill if you don't think about how you're routing. Now, one way that you can route without needing to back drill is as shown here on the left in the preferred method. Preferred method is usually pretty good up to, these 10, 20 gigahertz range. It depends on the leftover stub length here. But ideally, we'd like to minimize this stub length. And if we're routing to an internal layer, we could have a situation where the stub length is basically minimized down to this layer thickness of either one or two layers. So this is a good way to do this and eliminate the need for back drilling. The not preferred method, when you get up to really high frequencies, leaves these stubs and you just don't worry about it. And we'll see why this is bad here in just a moment. But this could be fine up to, low frequencies. I say about 5 gigahertz because, again, it depends on this stub length. Now, back drilled is an ideal case, and it would be great if it were less expensive. The problem here is that back drilling can leave behind 5 to 10 mil stubs. They can't go all the way up to this landing pad on the internal layer. And so the result is that if you have thin layer thicknesses over here, like let's say you're routing down to the second to the last layer and you have a 3 mil layer thickness, you're leaving behind a 3-layer stub. That means back drilling could leave behind a longer stub than this bottom layer thickness. So if you really need to ensure that stubs are eliminated, either route it like this or just go with blind and buried vias. So next, I want to talk about via impedance. This has been kind of a passion project of mine over the last year, as I've seen more and more companies release their via impedance calculator tools, which are actually producing incorrect results. So via impedance here is determined by the parasitics to the plane, the nearby plane, and you can see that here with these horizontal capacitors, and that's formed by the antipad. Then via impedance is also determined by its self-capacitance between the pads on the top and bottom layer, and then the via barrel has some inductance. And then, of course, there's a resistance here because the via is a conductor, and that conductor has non-zero resistivity, so there is some resistance along the length of this barrel. And then the stub can create deviations in the input impedance. So that input impedance is very important because it determines when we start to see dips in the return loss spectrum, as well as dips in the insertion loss spectrum. So let's take a look at an example here, okay? So here I've borrowed this graph from Bert Simonovich. I encourage you to go read this particular article by Bert. Very great explanation of stubs. And basically what he's saying here is that these stubs essentially act like partially open quarter wavelength resonators, okay? What is a partially open quarter wavelength resonator? Well, partially open quarter wavelength resonator basically means that at certain frequencies corresponding to 4x this length, so a frequency where the wavelength corresponds to 4x the length of this stub, at odd multiples of that frequency, you will start to see dips or strong losses in the insertion loss spectrum. And that is due to a 180-degree phase shift along this stub, which then creates destructive interference between the incoming signal and the outgoing signal or the reflected signal. Okay. So that means that you will then see these strong dips in this insertion loss spectrum if your stub is excessively long. Now, where do these dips start to occur? Well, you can see here that there is some f sub 0 frequency, right? Or when n equals 1, okay? Then it will appear at odd multiples of that, okay? So here at f1, and then 3 times f1, 5 times f1, so on and so forth, okay? So that's where you will expect to see all of these different all of these different dips in the insertion loss spectrum. So those correspond to very strong loss. And these can be bandwidth limiting. Basically, this can limit your available bandwidth down to what looks like a few gigahertz here. And basically, if you try to send in a signal with more than 3 gigahertz bandwidth, the channel will not function because the stub is blocking that power from getting down to the receive end of the interconnect. So how do we determine this effective dielectric constant to predict these frequencies? Well, it really depends on the geometry of the antipads, the separation between the two vias in the differential pair. And there's this nice result here from Bert Simonovich that gives you a way to calculate the effective dielectric constant that can then be used to predict these frequencies. Now, this L via is the length of the stub, and then this epsilon effective is this formula here, and it depends on all these geometric parameters. Here, it also depends on the transverse and the z direction values of the dielectric constant. Now, the transverse and z direction values of the dielectric constant mean the dielectric constant of the insulator, so of the dielectric, as measured in the in-plane directions, so the xy direction, that's the transverse, or in the z direction, so that's in the vertical direction. Okay, and those values are off from each other by approximately 20%. They may not even be reported in a data sheet, so that's really important. Now, there is some via delay that you can calculate once you know all of this stuff. So once you know this, you can then calculate what the amount of time is for a signal to transit this differential via. And then there's also a maximum kind of rule of thumb here based on the gigabaud rate. So the gigabaud, if you know the gigabaud rate for your particular interface, you can estimate what the maximum length of that stub should be. And of course, we have higher gigabaud, then we would of course expect lower maximum length for the via stub, just like we would expect. Now, I want to get into a pretty typical model that's used to describe via impedance. Now, the reason I bring up this model, despite the fact that it's wrong, is of course for your own information, but it's also because there are companies who have put out their own via impedance calculators that use this model. And this model is objectively wrong in the frequency ranges where it actually matters. So I don't want to call those companies out specifically by name. I'm always hesitant to do that in presentations. However, if you want to know which companies I'm talking about, you can go ahead and send me a message on LinkedIn, and I'll give you my thoughts privately. But basically what the lumped element via impedance model does is it models a via as a pi filter, as you can see here. And we have a trace connection on each side, and then we basically just need to calculate what is the capacitance and inductance of that via, and then you can do that using some via dimensions. What's the pad diameter, what's the antipad diameter passing through the plane, and then what's the via length. Here in this model, we only have one antipad. However, if you look back at this graphic, you could have many antipads. So that's one reason that this model has limited applicability and only considers one passage through a plane. And then once you have the L and the L and the C, you can then get a Z value. And then you can even predict a cutoff frequency and a propagation delay across this via. Now, the problem with this model, first of all, is that it grossly overpredicts the propagation delay through this via. Like, we're talking factor 5. So if you don't mind that your propagation delay prediction between top and bottom of your via is 5 times as large, then that's okay. But the first thing that it does is it incorrectly predicts via delay. The other reason that it fails is that there's no frequency dependence. And as we just saw in the case with stubs and in the examples I've shown earlier, there's always frequency dependence on the impedance. And we know that there's always frequency dependence on impedance because otherwise we wouldn't have these dips, these peaks and valleys in the return loss spectrum. Also, there's no consideration of resonant modes, which happens when the via starts to stops behaving as a quasi-TEM via and starts behaving as an actual resonator, which actually does happen within the bandwidths associated with 224G PAM4 signals. The other thing, of course, it's unable to account for things like stubs, blind and buried stacks, staggered. So, it's not very good for that sense. And it's only good for single-ended vias. So that's the other thing. We're talking about differential pairs here. I've seen calculators attempt to apply this to differential vias. And of course, they get it incorrect. Next, the author of this book who came up with this model, he actually tells you that it's incorrect. So he's literally telling you that when you shrink the signal rise time to a very small value, such that the value is comparable to the via delay, meaning that this via is now electrically short compared to the signal, well, electrically long compared to the signal. Now the signal behavior becomes extremely complex. So what he's referring to is the excitation of resonant modes and the frequency dependence. And he's basically telling you that second, whatever you do, it won't work very well. To precisely predict the behavior, you need a much more detailed model. And you should circumvent both problems by using a smaller via. So he's telling you right here that this model is incorrect in the instances where the via impedance actually matters. So how do we know when via impedance actually matters? Well, here, if we just look at this example with a single via passing through a pair of planes in this 6-layer stack up, going from the top layer to the bottom layer. Here you can see we have an antipad and we have a pad size and we have a via barrel size. And we can see where we start to see the deviation from the predicted input impedance from the LC model. Now, remember, the LC model is calculating a via impedance, but looking into the left side of this via, you actually have an input impedance where the trace is your load. So you can calculate the input impedance just based on the length of the via. And then eventually, as the signal bandwidth starts to increase beyond approximately 3 gigahertz, now you start to see a big deviation in the via impedance. And so the via impedance actually starts to get very large due to the inductance of this via. And so this is the type of behavior that the LC model simply can't predict. So the via is essentially invisible in the frequencies where the LC model is accurate. That's very interesting, right? It's basically saying within this frequency range, you could basically calculate whatever via impedance you want. And that via is going to appear mostly invisible as long as it's not too long. Now, eventually, the capacitance between these pads and then the planes takes over, and then we start to see a big dip in the impedance down to very low values. And then eventually we hit this limit here called a localization limit. And at that localization limit, this via starts to radiate very strongly. So you start to get strong radiation through the substrate out through the edges or towards the edges of the PCB. So what do we do about this? How do we contain this? Well, when we have just a single via, what we can do is we can use stitching vias. We can put stitching vias around this. And this stitching via array will overcome the inductance by applying some capacitance at lower frequencies. And then here we've basically created an inductive structure, so like a coaxial structure at higher frequencies. So that overcomes the high frequency capacitance. Then you can see here that we get this nice smooth line all the way out to about 44 gigahertz bandwidth limit. And at about 44 gigahertz, it starts to radiate. So this type of interconnect would be totally acceptable for a 112G PAM4 signal, because 112G PAM4 has bandwidth at 26 gigahertz, right? Or it has Nyquist frequency at 26 gigahertz. So we at least need to maintain flat impedance up to that Nyquist frequency. Now, here with this via structure, we've got a little bit small clearance here between this trace and the via. So, of course, there's some optimization that needs to happen to ensure that this is actually manufacturable. But just as an instance of getting started with a design, this is a pretty good way to go. And this illustrates that it is possible to get these flat bandwidths out to very high frequencies. Now, remember, we're dealing with differential pairs. So where's our differential via? Well, if you remember what I said earlier, you don't have to route the traces directly next to each other in order to get the signal down to the receiver. You could have a second via structure like this for your complementary signal in your differential pair. So you could actually take the differential pair, break it off, route into this kind of via structure, and then bring the two traces back together on the other side of this via structure, and then route those over to the receiver. So here's another instance where we have differential vias, meaning the two vias are brought close to each other and then routed through the stack up. And then these are basically targeting a very high speed interface at 25 gigabits per second NRZ signaling. So this is two-level signaling. So it's slower than the speed limits we're targeting with some of the design device I've been talking about. But basically what they did is they just sized an anti-pad like this, and then they threw some vias around it, kind of like this. One of the reasons they put the vias here is because they have these pads. And so, of course, they want to make sure they have a ground connection to those ground pads. Unfortunately, what happens here is you get insertion loss deviation. So this shows you what can happen when you have excessive you get a return loss deviation. So this shows you what happens when you have excessive return loss. And basically what this via is doing is it's limiting the bandwidth to about 5 gigahertz. So this type of structure would only be suitable for 10 gigabit per second NRZ signaling. It would not be suitable for 25 gigabit per second NRZ signaling. And that's because the 25 gigabit per second NRZ signaling has a 12.5 gigahertz Nyquist frequency. And so you can see here that our return loss gets a little too high at that frequency. So we would like to have the situation where our return loss spectrum is below negative 10 dB all the way up to our bandwidth limit. And that's a pretty good rule of thumb. Now, for standardized interfaces, like I said, negative 10 dB limit is a rule of thumb. But the standardized interfaces may actually specify an S parameter mask. And so they'll basically have a region where you can't have the curves pass through in order to ensure proper functioning of the interface. So now let's look at another fun example with a connector module targeting 224 gigabits per second PAM4. So this example shows what happens in a couple of situations where we are using blind and buried vias to route 224 gigabit per second bit streams with PAM4 modulation between two identical connector modules. So here I have the connector module that's been designed down here. I then put the complementary connector module at the load end, just as an example. And then here we're looking at what happens when we route below this thermal attach pad on layer 2 for our connector module. So the connector module attaches to these two pads. We want to route below that. And then what happens also when we route on an inner layer when we're not below this thermal attach module. So this thermal attach pad right here for the module does create an impedance deviation on L1. And you can see that right here with these error symbols showing about a 20 ohm impedance deviation, even in this small region. So that's pretty intense. However, if you look back here, we can see that with our target impedance of 90 ohms, it is possible to get reasonably close with these blind vias. So you can see here we have about 71 ohms looking from the top down, and then 87 looking from the bottom up. So here, when we route below the thermal attach, we're just barely compliant. I mean, just barely. And then we've got a little bit of excessive loss here right at the frequency limit. But we still have an open eye. So this should illustrate the various ways that we're going to qualify these different channels. We do want to look at the S parameter spectrum because the S parameter spectrum is going to tell us whether or not we have sufficient bandwidth up to our target frequency so that our receiver can interpret logic signals from this bit stream. But we also want to make sure that we have low noise and that we have an open eye. Eventually, as this interconnect gets longer and longer, and as we have more skew, the signals would start to overlap each other such that this eye or this vertical distance starts to close, and it becomes much more difficult to resolve the different signal levels in this bit stream. So what happens if we avoid the thermal attach? Well, if we route between the thermal attach, so basically this interconnect over here, if we route between the thermal attach, we could see that we are just below the 10 dB limit, all the way up to our target bandwidth. And then we get slightly lower loss. So it is possible to use blind vias to target these very high frequencies. And in fact, if you start to look at what some of the connector manufacturers do for guidance on their land patterns, they also recommend blind vias. And they basically recommend like a blind via with these blind stitching vias in order to give you a bandwidth limit all the way out to in the 90 hertz or 90 gigahertz range. So it is possible to design those interconnects that way. Next, what happens if we go through the internal layer? So the internal layer with the stacked and staggered blind and buried vias, it can give you these very good return loss spectra, even all the way up to these very high bandwidths. So this is one of the gold standard via stacks that was designed for this connector module. And this connector module is currently being manufactured at the client's partner in Japan. And we'll see what happens when it goes into testing, but the simulation results for some of these via structures look very promising. And you can just see that here from the return loss spectrum on the left, as well as when we look at the loss values and then we look at the eye diagram, the loss value it's a little high. However, the eye diagram is still open. So we could still route this over to a nearby connector module that could then take these signals into, for example, an active copper or fiber interconnect, and then transmit them over a cable backplane over to another module in a data center. So that's what I have for you guys. Thank you so much for attending and listening. It's always fun to talk about this topic.